Um, what I will be presenting today is some joint work with Sota Asai, Osamu Iyama, and Kaveh Musafand. Um, so it started. All of us have been interested in tau tilting theory, torsion classes, and the relationship with bricks. Because, well, I'll be talking about bricks as well. Well, you can see it in the title. And we started looking at, I would say, some brick analog of the classical notion of splitting torsion classes, and we started realizing that this notion has some deeper connection to other areas, and this is where it started. I'll be giving a lot of definitions. So if you don't know what a brick is, if you don't know what a torsion class is, I'll define those. So if you have any questions at any time, just feel free to interrupt. Okay, so I'll be starting with the basic settings of the talk. So K will be any field. So a priori, I don't need any special assumption on K. A is a finite dimensional associative K algebra that we'll just assume to be basic for simplicity. So you can think of A as being given by a finite quiver with an unmissable ideal, if you like. And mod A is the category of finitely generated or finite dimensional left A modules. If you prefer right A modules, you can take right A modules. You just need to fix a sign. So I'll cover 5 sections. So first section, I'll just recall the notion of torsion class, torsion pairs, and the classical notion of splitting. Then we'll look at the brick analog of those notions. And then I'll jump into some lattice properties of torsion classes. That should lead us to this new notion of brick-directed algebras, so in section 4. And finally, in section 5, I'll present the main theorems and certain ways to characterize these new algebras, the brick-directed algebras. Okay. All right. So I'll start with the definition. So all categories will be full subcategories of the module category mod A. And such a full subcategory is said to be a torsion class. So a torsion class is a full subcategory that is closed under extensions. So if you have a short exact sequence and the first and the third terms are in your category, then the middle term has to be there, and it has to be closed under quotients. So this is for a torsion class, and if you want a torsion free, you ask that it's closed under extensions and subobject or submodules if you prefer. So you have these two notions, and each torsion class uniquely defines a corresponding torsion-free class. So they always come in pair, and this is called a torsion pair. So if you have a torsion class, then you can look at the right perp of that torsion class, and this is defined to be the set of all modules for which there is no homomorphism from the torsion class to that module. So that's the right home perpendicular category, T-perp. And the corresponding pair, we call this a torsion pair. So I could talk about torsion pairs for 20 minutes, but I'm not going to do that. That's not the purpose of the talk. So sometimes I'll refer to a torsion class And some other times I'll refer to a torsion pair, but it's really the same data because every torsion class uniquely determines a corresponding torsion pair, which is this pair right here. So let's recall this classical notion of splitting torsion pairs. So, or torsion class. So you can call a torsion class splitting if any indecomposable object in your module category is either torsion or torsion-free. So in other words, any indecomposable object is either in T or in the corresponding torsion-free class T-perp. Okay, so maybe some quick examples of splitting. So here I'm looking at a very simple algebra, the path algebra of the A3 quiver. Equivalently, you can think of it as the algebra of lower triangular 3x3 matrices with matrix multiplication. So over this algebra, you have only 6 indecomposable modules, which are represented by these 6 dots. And these arrows here, they represent some particular morphisms, non-zero homomorphisms between indecomposable that we call irreducible. So, for instance, for a torsion class, you would select to define a torsion class, I can tell you the indecomposables in that torsion class. And for instance, I can take only that object here, which is the simple module at vertex 1. And if you look at T-perp, the corresponding torsion-free class, you would realize that it would be generated by these 3 indecomposable objects. So these 3 objects are exactly the object which have no homomorphism from that simple module at 1. So the torsion pair here will consist of, on total, 4 indecomposable objects. And as you can see, this is not splitting because you're missing 2 indecomposables. On the other hand, you can say, here's another example. You could take T, your torsion class, to consist of these 3 indecomposable objects with the corresponding morphisms and direct sums. And T-perp, the set of modules admitting no home from T, then you're just going to get the complement. So in terms of indecomposable objects. And so in that case, you can see that any given indecomposable is either in T or in the corresponding T-perp. So this is splitting. Okay, so not every torsion class is splitting, but there are some ways to create splitting torsion classes. Okay, so two small examples. Now let me talk about bricks, because that would be used for defining the notion of brick splitting torsion classes. So recall what a brick is. So a brick is any module. We'll just restrict to finite dimensional modules. We can also consider infinite dimensional bricks, but for this talk, all modules will be finite dimensional. So a brick is just a module whose endomorphism algebra is a division K algebra. So the notation that we will use is brick of A will denote the set of isoclasses of bricks. So we take just one brick per isoclass and we collect them into a set. That would be a set. And so in particular, we can ask questions for the algebra. So do we have finitely many bricks up to isomorphism, in which case we will call the algebra brick finite? Or do we have infinitely many bricks up to isomorphism, in which case we would call the algebra brick infinite. So if you know about tau tilting theory, and I won't really need tau tilting theory in this talk. So having finitely many bricks is equivalent to being tau tilting finite, and infinitely many bricks is tau tilting infinite. But again, I won't need tau tilting theory in this talk. So I'm not going to discuss that any further. Maybe two quick remarks. Every brick is indecomposable, because if your endomorphism algebra is a division algebra, then you don't have any non-trivial idempotence, so that makes your module indecomposable. But in general, the converse is not true. So an indecomposable module is not necessarily a brick. Every simple module is a brick. This is by Schur's lemma. So you always have some bricks, at least the simple modules, but possibly other bricks. Now, I can define the notion of brick splitting. So brick splitting, you just take the classical notion of splitting torsion class and you replace indecomposable by bricks. So simply, a torsion class is brick splitting if any given brick is either torsion or torsion-free. So we're not interested now in all indecomposables, but only the bricks. And the reason why we looked at that notion in the first place is because if you know a little bit about tau tilting theory or torsion theory, you may know that bricks really control the torsion theory of an algebra. So it was making sense for us to just look at the notion of brick splitting. So look at the location of bricks inside our torsion theory. So some quick remarks. So the notion of splitting implies the notion of brick splitting simply because every brick is an indecomposable. So if your torsion pair splits the indecomposables, then it will also split the bricks. However, the converse is not true in general. And here's an example. So if you take the path algebra of this quiver, so one loop and one straight arrow, modulo all paths of length 2 are declared to be 0. So this is the quotient of a path algebra. We can create the following. So the torsion pair, I can take, in fact, I can take in it all modules having only the simple module at 1 as composition factor. And in fact, there are only 2 indecomposable modules with that property. It's the simple module at 1 that I denote by a 1, and some self-extension of that module that I denote with 1. So there are only 2 indecomposables in that T, and then you can check that T is closed under extension in quotients. And the corresponding T-perp in that case, it would just consist of the indecomposable modules having no simple module at 1 in their suckle. And in fact, you can check that the only indecomposables with that property is the simple module at 2. And this one here is actually the injective module at 2. And in this algebra, so this algebra is representation finite. It has only finitely many indecomposables. And in fact, it's also, so in particular, it's also brick finite. And there are only 3 bricks for this algebra. Well, the 2 simple modules that I denote by 1 and 2, and the injective at 2, which I denote by 1, 2. And as you can see, because we have only these 3 bricks, then this algebra is brick splitting. So 2 of the bricks are torsion-free, and 1 of them is torsion. However, this is not splitting, because if you look at the projective at 1, the projective module at 1 would look like this. So it's 3-dimensional. However, it's neither in T nor in T-perp. So this is not in the union of T with T perm. So because of that, you see that this torsion pair is brick splitting. So it splits the bricks, but is not splitting.
Oh, sorry, Charles.
Yes.
There is a question on chat.
Oh, sorry, I cannot see the chat. So yeah, for some reason I cannot see the chat because I'm sharing.
Maybe I
Can you
can
tell me
read for you. Why do you call this torsion classes splitting? My question is about the name.
We just rely on the classical name. So the classical notion was splitting because it splits in the composables into two categories, torsion and torsion free. That's where I think the name comes from. It just splits the thing into two categories. And when we just took the same name but add brick to it because what it splits is not the indecomposables now, it's just the bricks. So it's really just coming from the classical notion. Okay. Yeah, please let me know if you see any other, because yeah, for some reason, well, I need to hover my mouse on the bar in order to see the chat, but I don't see it
Yes,
by the.
I read for you if there is.
Okay, so in case the algebra is hereditary, we can say a little bit more about this relationship between splitting and brick splitting. So hereditary just means that, well, examples of finite dimensional hereditary algebras is just path algebra of a quiver, of a finite quiver without oriented cycles. So if you assume in addition that your torsion class is functorially finite, so functorially finite is, I'm not going to define, but basically it means that modules can have approximations on the left and on the right by elements of T. You can find some nice approximations. So a functorially finite torsion class is just a torsion class that is, better behaved in some sense. And so what we can prove is that if you have a hereditary algebra and a functorially finite torsion class, then brick splitting is the same as the classical splitting. So T is brick splitting if and only if T is splitting. So that would be a setting where these two notions would agree. But as we will see later, even for hereditary algebras, we can find a lot of non-splitting. Yeah. So we'll talk more about hereditary algebras in a moment on the next slide. Not yet on the next slide, but soon. So what I would like to do next is explain why having brick splitting would impose some condition on the quiver of your algebra. So if you have a torsion pair that is brick splitting, then you can look at the simple modules. And for any torsion pair, this is true that any given simple module will be either torsion or torsion free. So any torsion pair is like that, it splits the simples. So you don't need brick splitting. What I can do here is look at the simple modules that are in the torsion-free class, and I can look at the simple modules that are in the torsion class. So you can do that for any, whenever you have a torsion pair, you can split the simples like that. But what you can say when your torsion pair is brick splitting is that in fact, there would be no extensions between the simples in the first category, in the first set, to the simples in the second set. So if you think in terms of your quiver, you have the simples or the vertices corresponding to your torsion, and you have the simples or the vertices corresponding to your torsion free. So your torsion pair will always split your simples. And then what this proposition is saying is that the only arrows will go from left to right, because extensions between simples correspond to arrows in your quiver. So there's no arrow going in the other direction. So in other words, when you have a brick splitting torsion pair, it would give you a block triangular decomposition of your algebra, which means exactly this, that you can split the vertices into two categories for which there's no arrows from one set to the other. And of course, that's only interesting in case where these two sets are non-empty. But if say S1 is empty, then that means that all simple modules are in T, in which case T coincides with the whole module category. And if S2 is empty, then that means that your torsion class is just zero. So we call them the trivial torsion classes when you get either zero or the full module category. So that's not a very interesting case. But other than that, you will always get this block triangular decomposition. And so as a consequence, so if you have an algebra for which there's no way to find this block triangular decomposition, then you know that there won't be any non-trivial brick splitting torsion classes. So for instance, if your algebra is connected self-injective, and it's not hard to prove that in that case, there's no way to find a block triangular decomposition of your algebra. So therefore, if your algebra is connected self-injective, then the only way to find a brick splitting torsion pair is when you take zero for mod A. So that would be when one of the two sets, one of the two sets here is empty. Okay, so let me now discuss some lattice properties of torsion classes. So we can collect the set of all torsion classes in mod A. So that's a set. But not only it is a set, but it is a poset if we order the torsion classes by inclusion. This is a partially ordered set. And not only it's a partially ordered set, but it's a lattice. So that means that we have these two operations called the meet and the join. So the meet of two torsion classes is simply given by the intersection of these two torsion classes. So it's not hard to check that if you take the intersection of two torsion classes, then it's again a torsion class. So it is closed under extensions and under quotients. However, when you take the union of two torsion classes, then this is not necessarily a torsion class, but you can define the join of these torsion classes as being, in fact, there is a unique way to consider. So you can take the smallest torsion class containing the union T1 union T2, and there would be so this is actually well defined, and you can define this as being the join. So the meet is the largest torsion class that is less than or equal to both T1 and T2 with respect to your partial order. And the join is the smallest torsion class that is bigger than or equal to both T1 and T2. And so that's how you get these two operations. And that makes tors of A a lattice. So when you have a lattice or any partially ordered set, you can consider its Hasse diagram. So the Hasse diagram is just a diagram to help you understand the structure of your poset. And so in the Hasse diagram of a poset, you would put an edge for every cover relation. So a cover relation is when you have a strict inequality between two elements, but there's no other elements in between. So this is a cover relation. And it turns out that for the lattice of torsion classes, cover relations are well understood. So this was studied by Barnard, Carroll, and Zhu, but also by Demone, Iyama, Reiten, Reading, and Thomas. So the brick labeling. So if you have a cover relation, so that means here that T is less than T prime. So T and T prime are two torsion classes. So T is less than T prime, but there's no other torsion class in between. So this is a cover relation. And so we can associate to this cover relation a brick. And this is actually the unique brick. This is the unique brick B, which is in the largest of the two torsion classes, and which is torsion free with respect to the smallest of the two. So remember that to T, you can associate the corresponding torsion free class, which is T perp. So this is the unique brick that is torsion free with respect to the small one and torsion with respect to the big one. And so there is this unique label that you can put on this edge. This is called brick labeling. So brick occur very naturally in the Hasse diagram of the lattice of torsion classes. So I will have to use that next. So our first theorem is a way to characterize the notion of brick splitting in terms of these labeling. So what happens is that so let me first explain on a picture. So if you have a brick splitting torsion class, then you can compare it with the smallest torsion class, which is 0, and the largest torsion class, which is the big module category, mod A. And so that would give you two intervals. The interval, so of all torsion classes between 0 and T, and the interval of all torsion classes between T and mod A. And of course, that does not necessarily cover all of tors A. There might be things that are not comparable to T. But so our theorem says that if T is brick splitting, then if you look at the labels, the brick labeling of the interval 0T, together with the labels, so the brick labelings of the interval from T to mod A, then you recover all bricks in this way. And conversely, if you look at the labels of these two intervals, and if that gives you all bricks, then you know that your torsion class is brick splitting. So in other words, if I have a brick splitting torsion class T, then I look at these two intervals. I look at elements comparable to T. So that gives me two intervals. And I know that any brick that you give me will appear as a label somewhere, either as a label for this interval or for that interval. Okay, so that's one way to detect brick splitting. And a corollary of that is the following. So imagine that your algebra is brick finite, so you have finitely many bricks. So if in tors of A you can find a chain whose length is the number of bricks, then you know that all torsion classes on that chain will be brick splitting, because in that case, so if you can find such a chain, so you would have a chain where you can find, I mean, whose length is equal to the number of bricks. So you could look at the bricks appearing over there. So suppose you have or many bricks. So there is so if you look at the labels on a given chain, you can actually prove that bricks on a given chain cannot be isomorphic. So if you have such a chain, that means that you have all bricks appearing on that chain, and therefore you can apply the previous theorem. So if you take any given torsion class on this chain, then it's obvious that any given brick either appear as a label of the interval 0t or as a label of the interval t2 mod a, because you get all bricks on that chain.
Sorry,
So
Charlie.
so,
Another
yeah,
question.
yes.
Is it possible to that a break appear in a as a label of 2 times or more?
Yeah. So in general, that would happen. Yeah, a given brick may appear as a label multiple times. Yes. Yes.
Oh, thank you.
Yeah, well, as a very easy example, if you, yeah, so if you look at this algebra, so quiver A2, so the torsion, the lattice of torsion class would look like this. And so the simple at 2 would appear here. That would be the label of these two edges. And the simple at 1 would appear as the label of these two edges. And the projective at 2 would appear as a label only of this edge. But that on that example, you can see that you have exactly 3 bricks. And here you have a chain where all bricks appear, right? So you know you are guaranteed by this corollary that all torsion class on this chain will be brick split. But on this chain, they do not all appear. So if you take T to be here, then it's not true that any given brick appear as a label for the interval 0t or t mod a. So you know that this torsion class is not brick split. Yeah, thank you for the question. Yeah, so in fact, we can find a completely lattice theoretical way to characterize brick splitting. So for that, I need to recall the notion of left modular element in a lattice. So if you have any lattice, so a poset with a meet and a join, so you can call an element x in your lattice left modular if you have the following condition. So for any two comparable elements, y is less than z, you need to have this equality. So in fact, you always have, let me check which one it is, you always have an inequality. So for any two elements, y less than z, and for any element x, you always have that y join x meet z is always less than or equal to y join x meet z. But when this inequality is an equality for any two pairs, then you'll say that x is left modular. So x satisfies the left modular identity. So this is how it is called. As we will see, this notion of left modularity is closely related to the notion of brick splitting. So let me actually use the same example I just used. So the path algebra of the A2 quiver. On the previous slide, I drew the lattice, but in fact here, let me use some easy names. So let me call the minimal element 0, the maximal element 1. Let me call this element x, this element y, and this element z. So you can think of them as being 5 torsion classes. There are exactly 5 torsion classes for this algebra. So x is not left modular. Why? Well, if you take y less than z, so here y is less than z on this example, if you compute y join x meet z, then y join x, y and x are here, so their join is the smallest element that is greater than or equal to both of them, so that would be the maximal element. And maximal element meets z would simply be z itself. So that's the left-hand side. And if you look at the right-hand side, so what is x meet z? Well, x meets z is the largest element that is less than or equal to both x and z, and that's the minimal element 0. So you get y join 0, and y join 0 is simply y. So as you can see, the right-hand side is less than or equal to the right-hand side, but they are not equal. So, so x is not left modular. But if you look at the other elements of your lattice, so 0, y, z, and 1, and all of these other elements are left modular. So checking left modularity might seem quite hard because you need to look at this condition for any given pair of elements y less than z. So a priori, that could be quite long to check. But for the lattice of torsion classes, it turns out that we have this very simple answer. So if you have a given torsion class of any finite dimensional algebra, then brick splitting is just the same as left modularity. So returning to the A2 example, so we know that if we take this torsion, this post set of torsion classes, then the brick splitting torsion pairs are all of these 4 torsion classes appearing on this maximal chain because they are all left modular. So this leads to the notion of brick-directed algebra. So in the past examples I've shown you, there was always a chain, in particular in the A2 example, there was always a chain of torsion classes where all bricks would appear on the chain. And in fact, if you have a chain of torsion classes with brick labelings on it, then you can actually prove that there is no homomorphism from a brick from any given brick on that chain to a brick that appears higher up in that chain. So in fact, so if you have this chain of torsion classes, and you have these labeling bricks, B1 all the way to BR, then you always have this condition that home BI, BJ is equal to 0 when I is less than J. So this is automatic for any chain and for any sequence of labels that you see on that chain. So as I said on the previous example, we always had this chain where all bricks would appear. And so if we have such a situation, that means that we can order the bricks so that there is no home in one direction, which is a very interesting condition to have for an algebra. So based on this, we will define the notion of brick-directed algebra. So a brick-directed algebra is any algebra for which you have no brick cycle. So in other words, this is any algebra for which there does not exist any cycle of non-zero non-isomorphisms between bricks. So this is the analog of the classical notion of representation-directed algebras. So if you know about them, so representation-directed algebras are very useful for instance, for understanding representation finite algebras. So they have appeared a lot in the literature. And this is just the brick analog of this classical notion of representation-directed algebra. So representation-directed means you have no oriented cycles of indecomposables, and brick-directed is just you have no oriented cycles of bricks in your module kit. And if you look again at a situation like that, if you have a chain of torsion classes where all bricks appear on that chain, then you will be in this situation here of brick-directed because this chain forces this home condition on bricks. So here are a few examples of brick-directed algebras. First of all, you have representation-directed. The Kronecker quiver or the Kronecker algebra is brick-directed, in fact. So that's interesting here because this algebra is not representation finite. It's not even brick finite, but it is brick-directed. So you cannot find any oriented cycles of bricks. The notion of brick-directed is close undertaking quotient or undertaking wide subcategories. So any quotient of it will again be brick-directed. Or if you know about tau tilting reduction, so a tau tilting reduction would also be brick-directed. You can glue brick-directed algebras together to get a new one. So for instance, if you take two copies of the Kronecker algebra and you glue them in this very specific way, where by gluing we impose all quadratic relations at the node of the gluing, then again you would get a brick-directed algebra. So that we have some general recipe to construct like a large family of brick-directed algebras. So there are quite a lot of them. But so if you restrict to hereditary algebras, then brick-directed are quite specific. So here's one proposition. So if you have a hereditary algebra, so just think of it as the path algebra of some quiver. And let's assume that the quiver is connected. Then brick-directedness is the same as saying that your quiver is either Dynkin, because, well, in that case, it's just representation-directed, in fact, so it will be brick-directed, or you have the Kronecker quiver, and that's it. That's the only examples of brick-directed hereditary algebra. So if you take extended Dynkin quiver that is not Kronecker quiver, you can actually always find a cycle of bricks. So that won't make your algebra brick-directed. Another proposition, strictly wild algebras. So this is a stronger notion than the notion of wild algebra. So a strictly wild algebra is just any algebra for which you can fully embed the module category of the three-Kronecker algebra into it. That's one way to define strictly wild, and any strictly wild algebra will not be brick-directed. So you don't need hereditary for that result. So in the next 5 minutes or so, I'd like to talk about some characterization of brick-directed algebras. So in general, we have this way to characterize brick-directed algebras. So I mean, you can already guess why 1 and 2 are equivalent. So 2 is just saying that so brick-directed is equivalent to having a total order on your bricks such that you have no home in the forward direction. So this is a phenomenon that we already observed. But what is very interesting with this theorem is that you can translate this notion of brick-directed to a notion about the lattice of torsion classes. So an algebra is brick-directed if and only if you can find a maximal chain in the lattice of torsion classes where all torsion classes are brick splitting over that maximal chain. So in fact, remember that whenever you have a non-trivial brick-splitting torsion class, that induces some block triangular decomposition of your quiver. And if you have a brick-directed algebra, so using part 3 of the theorem, that would actually give you many block triangular decompositions of your algebra. And in fact, that would force the quiver of your algebra to be almost triangular. So in fact, in this corollary, so if you have an algebra that is brick-directed, then the algebra is weakly triangular, which means that its quiver is almost acyclic. So it looks like some acyclic quiver, so no oriented cycle, other than loops. So if you remove loops, you would get some acyclic quiver. So that means that the quiver of your algebra would look like this one here. If you have a brick-directed algebra. So let me talk a little bit about lattices in the last few minutes. So if you have any finite lattice, and let me just restrict to finite lattices. So I see a question here. Is the order on the bricks with respect to the AR quiver? It depends. I mean, AR quiver may, I mean, if you have a brick-directed algebra, it could be brick infinite. So you also have to look at morphisms in the infinite radical, which will not really be captured in the AR quiver. But somehow, yes. So if you have like a representation finite algebra, I mean, the AR quiver may still have some oriented cycles, but when you just look at the bricks, you won't be able to form a cycle over there. So I mean, yeah, there are some link with the AR quiver, but you have to be careful because you want to consider all morphisms, not only those given by the arrows in your AR. So yeah, let me go back to these notions. So if you have a finite lattice, so for instance, if your algebra is brick finite, you have the notion of join irreducible and meet irreducible.
Sorry, Charlie, there is another question on the chat. Yes. What is the order on the breaks?
Oh, it's okay. Let me go to the previous page. This order here, right? It's just a theoretical order that would satisfy this condition here. So I can find a total order. So I have a way to totally order the bricks so that when I go from smaller to larger, I have no homomorphism between them. But that order is not unique. It's just any total order that would satisfy this. And in fact, if we have that order on bricks, we can use that total order to get a chain of brick splitting torsion classes. So there is actually a link between that total order on bricks and the order induced from this chain of brick splitting torsion classes. Okay. So yeah, here we have join irreducible elements, meet irreducible elements. The definitions are given. And if you have a lattice, you can also consider its length, which is so again, a finite lattice. This is the maximal length of a chain that you will have. And so very quickly, so in general, the lattice of torsion classes is not distributive, but it satisfies a weaker notion than distributive, which is called semi-distributive, which I'm not going to define. And in fact, so there is this nice property of a distributive lattice, which says that if you look at the join irreducible elements and the meet irreducible elements, they would have the same size. And the size of that would coincide with the length of any maximal chain. And of course, if you have a semi-distributive lattice, you should not expect this property to hold. But for a brick finite algebra, we always have an equality on the sizes of these three sets. And in fact, that motivates the following definition. A lattice is said to be extremal if the length of the lattice coincides with the number of join irreducibles and the number of meet irreducibles. So this is close to being distributive, but not yet. And in that case, you can define the spine of your lattice to be the set of all elements which lie on a chain of maximal length. So this is just purely combinatorial notions on lattices, so extremality and the spine. And you can call a lattice to be left modular if you can find a maximal chain of left modular elements. So the picture looks like this. You have distributive lattices. Every distributive lattice is extremal, and also every distributive lattice is left modular. But in general, modular and extremal do not coincide. But it turns out, and let me finish with that, that for brick-directed algebras, these two notions are the same and they're all equivalent to being brick-directed. So that's the main theorem, which actually we state for brick finite algebras, but there is a way to extend it to all algebras. So brick directedness is the same as left modular, which is the same as extremal. And in that case, the spine of your torsion class would be the set of all brick splitting torsion classes. Okay, I just finished with this by showing some remarks. So I'm already over my time, so I'll finish here. Thank you.
So thank you very much, Charlie. Thank you for your very nice talk. Are there any questions or comments?
I have a question. Yes. Could you
Yes,
show it again? Why for the self-injective algebra the brick splitting torsion class is trivial?
For self-injective?
Yeah. So you give a corollary for the self-injective algebra, then the only possible brick splitting torsion class are the trivial ones.
Yes. So let me go back. Where is this?
Previous, I think.
Okay, right.
Yeah, this
Right.
one. Yes. So
Yes.
why?
Yes. 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 Mm-hmm. Yeah. So in fact, so if you have a connected self-injective algebra, the idea is that you cannot have such a structure. So there's no way to find a block triangular decomposition of a connected self-injective algebra. Because if you do have that, remember that over a self-injective algebra, every projective is injective, every injective is projective. So you can look at the, for instance, at the injective and the composables of these vertices, and these injectives will be supported over this region. So they would have to coincide with projectives starting here. And if you make the count, you would actually find that there is a problem. So that would lead to a contradiction. So in fact, yeah, so every self-injective algebra that is connected cannot have any decomposition like that. And as we have seen previously, if you have a non-trivial brick splitting torsion class, it would always give you a decomposition like that.
Okay, thank you very much.
I have a couple questions, if I may.
Yes, please. Yeah.
Okay. First of all, Charles, thanks for the very nice talk. Related to the previous question about brick labeling, is it possible for one chain to have repeated bricks, a single chain?
No, it cannot happen because if you have a given chain, so let's say I have a brick B1 here and a brick B2 here. So on a given chain, you always have this forward vanishing of home spaces. So home from B1 to B2 would be 0 if you have two labels like that on a given chain. So they cannot be isomorphic because there's no home from one to the other.
I see. Thank you. Another question is, if you could please go to the slide with this result about brick splitting torsion classes and the extensions, which vanish. Oh, yeah, actually a bit higher up.
Oh, yes.
Yeah, there we go. There we go. Yeah. So does this imply that all brick splitting torsion pairs are functorially finite? By taking exact sequences?
No, they're not necessarily. Wait, let me think for a moment. Are they always functorially?
I guess it depends on how this. No, go ahead.
Yeah, so for instance, if you take the Kronecker algebra, so you probably know the representation theory of the Kronecker algebra. So
Yep.
if you take a quasi-simple in a tube, so you can look at the torsion class generated by that quasi-simple. So it would actually give you that tube together with all pre-injectives. And the corresponding torsion free class would be the other tubes with the pre-projective. So that would actually be splitting and even brick splitting, but it's not functorially finite.
Of course. Thank you. And one last question. At the end of section 1, you mentioned, if you could please go back.
Section 1, yes, here.
Yeah, you made a remark about how torsion, in general, torsion classes can be made to be splitting. If you could maybe elaborate a bit more on that. I think you mentioned there's a way to, given any torsion class, like apply some procedure to turn it into a splitting torsion class.
No, yeah, actually, this is not what I meant. It's just that I mean, in some particular setting, we have some nice way to create splitting. Like, for instance, for hereditary algebras, because we know the. I mean, going back to the AR quiver for hereditary algebras, we know very well the AR quiver and also the morphisms between components. So in order to get a splitting or brick splitting in that case, so because splitting implies brick splitting, we can just like somehow find a slice in the quiver and say, well, everything on the right of that is in my torsion class, and everything on the left is torsion free. So a little bit like in this example here, I took my torsion to be something that is closed under successor, and then everything else will be torsion free. So that's some general recipe to construct splitting. But over an arbitrary algebra, there may not be any splitting torsion class.
I see. And one last question, a follow-up question. Do you have any nice setting in which any torsion class can be turned into a brick splitting class? Maybe a bit more general than this.
So in fact, we have a way to construct all brick splitting torsion classes. So yeah, there are a couple of things that I did not mention. Let me go to the last page. So I did not cover that. But so what you can do is you can actually look at what we call the brick quiver of an algebra. So the vertices of this would be given by the bricks up to isomorphisms. And you would put an arrow from brick B to brick B prime simply if the home from B to B prime is non-zero. So if there is a home from one to the other. And in fact, we can prove that there is a one-to-one correspondence between brick splitting torsion pairs and successor closed subquivers. Okay, maybe I call this theta A. So successor closed subquivers of theta A. So in some sense, that gives you a recipe. So if you look at your arbitrary torsion class, you can look at the subset of the corresponding brick quivers that it represents, and then you just close that under successor. And that would give you brick splitting. But of course, if you start with an arbitrary algebra, if you close under successor, that may just give you all bricks, and that would just give you the entire module category.
I understand. Thank you very much.
So, Charlie, there's 2 questions on the chat. Can you see it? Or
yes, I can now see them. Okay, is it possible so that a semi-stable torsion class to be brick splitting? Yes, well, it depends on the semi. So by semi-stable torsion class, I think you probably mean these torsion classes. So if you have a stability condition theta, then you have 2 torsion classes that you can associate to that. So T theta and T bar theta. Yeah, so sometimes they are brick splitting and sometimes they are not brick splitting. So an interesting question could be, so if you have a brick-directed algebra, under which conditions such a torsion class is brick splitting? I don't know the answer of that precisely, but in fact, there is one slide that I skipped, which is this one here, and we have some geometric characterization of brick-directed algebras in terms of semi-stability, which is not exactly what you're asking, but very roughly here, I did not cover that. But in the brick finite case, at least, so brick directed is the same as being able to order the walls of the semi-stable of this, of the wall and chamber structure of semi-stability conditions for the algebra. So it is equivalent to being able to order the walls in some way. So that there is some link with stability. But yeah, so if you give me an arbitrary torsion class coming from stability, it's not clear if it's brick splitting or not. It may be brick splitting, it may not be brick splitting, but I don't think it is in general. I see another question. I think if theta is brick splitting, then theta must be in the G-fan. Not necessarily, in fact, because like again, if you take the Kronecker quiver, if you take theta to be the only element that is outside of the G-fan, so theta is equal to 1 minus 1, then T theta would be all pre-injectives. And the corresponding torsion free will be the rest. So it would be brick splitting. And if you take T bar theta, then that would be all regulars together with all pre-injectives. And corresponding torsion free will be all pre-projective. And that's brick splitting again. So yeah, so it's you may have things outside of the G-fan that still give you brick splitting. And if the algebra is not brick directed, you could have things in the G-fan that do not give you brick splitting. However, if the algebra is brick directed, and if you take a theta in the G-fan, even in that case, it's not necessarily brick splitting. In fact, yeah. I don't know if that answers your question.
So thank you. And Charlie, I have also one question. In your proposition, it says that if we have a break splitting torsion, then we have some nice splitting of the simples. And what about the converse? If we have some such condition, is it possible to construct break splitting by using this simple?
Yeah, in fact, to split the simples, you do not need brick splitting, because if you have so in fact, if you have any torsion, okay, so if you have any torsion pair, so if you have any module, including a simple, you have this canonical short exact sequence. So where here you take the maximal submodule of S, which is in T. So that would be a torsion submodule. And here you take the quotient of that. So you always have this short exact sequence. And so if you start with a simple module, then because it is simple, then because it is simple, then this thing is either 0 or itself. So if it is itself, then that means that the simple is already torsion. And if it is 0, then that means that the simple is isomorphic to this one, which is torsion-free. So if you have any torsion pair, a given simple always fall into either torsion or torsion-free. So you always split the simple. So what is new with brick splitting, this new phenomenon, is that if you have an extension between two different simples, so if you have a short exact sequence like this, where S1 and S2 are non-isomorphic simples, then in fact, this middle term is a brick. It's always a brick if the two simples are non-isomorphic. And so if it is brick splitting, then this thing here is either torsion or torsion-free. And if it is torsion, then there's no map from torsion to torsion-free. So this S2 cannot be torsion-free. And if it is torsion-free, so if E is torsion-free, then again, there's no home from torsion to torsion-free. So S1 cannot be torsion. So that gives you some strong conditions on where S1 and S2 could be. So that's how we prove this condition here. But again, the splitting on the simples is just automatic from having a torsion pair.
No, it means by also extension. It means if you have a such shape in a quiver, we have a two part in a quiver. Is it possible to construct a splitting, break splitting torsion or not? Because the quiver of the algebra is very nice in this case. We have some part and some part we have arrow from one direction.
Yeah, in fact, I think it's not always possible. Let me. Yeah. So let's say your quiver looks like this. Yeah. So if your quiver looks like this and you have some relations.
Yes.
So if you want to split, the only way you could do that in some non-trivial way would be to take T to have simple at 1, simple at 2, and to take T perp to have simple at 3, simple at 4, because you have oriented cycles otherwise, and the other direction is not possible. There's no arrow from. And so if you take the brick corresponding to this string, you can define a brick like that, where as a representation, you would put a one-dimensional vector space at all of these vertices and identities. So if you look at that brick, so if it is brick splitting, so if your torsion pair is brick splitting, then this brick is either torsion or torsion-free. But if it is torsion, then it's closed under quotient, and that would force the simple at 4 to be torsion, and it's not torsion. And if it is torsion-free, then it's closed under submodule, and then it would force this one to be torsion-free, but it's not. So there are some configuration that would not allow brick splitting, even if you have this nice triangular decomposition.
Yeah. Thank you. And the other question is that you say that if we have a break splitting, then all breaks appear in a interval 0 and Tn mode. But is there some condition for breaking finite algebra which guarantees the existence of non-trivial break splitting torsion?
Yeah, this.
Because if you have such condition, then we can study the break by just using these two interval. And
so you want a condition for brick finite algebra so that
you did
you have
infinite algebra.
a brick infinite algebra.
Yeah,
for
brick
which,
infinite.
Yeah, for brick, I mean, it also works for brick infinite, but of course for brick infinite you have infinitely many labels, so
Infinitely many,
it's
yeah.
not like a finite condition to check. So yeah, so the answer I would give is what I told Diego earlier, is that we have this systematic way to construct brick splitting by taking successor closed set of bricks. I could add that in the rank 2 case, so whenever the quiver has, so if you are in rank 2, I mean, in order to have non-trivial brick splitting, you need all arrows to go in a given direction, right? So any rank 2 quiver that would have a quiver like that would have many brick splitting torsion classes, because the lattice of torsion class will always look like that.
Infinitely.
And then you have something in the middle that might be quite complicated. But in that case, everything here, they would all be functorially finite torsion classes, and also everything here would be brick splitting. Yeah, if you have too many arrows in the middle, it won't be brick directed. So even though you'll have many brick splitting torsion classes, it won't be possible to find a big chain for which all bricks would appear.
Yeah, thank you. So
yeah, I feel that we understand brick directed and brick splitting quite well, but it is still mysterious. It's not like it's not always clear to detect how or when a given algebra is brick directed.
So thank you very much.